Just before 4 in the morning on Wednesday, the 3rd of June 2026, the seafloor off the far northern coast of California lurched. A magnitude 5.7 earthquake broke about 100 miles out from Crescent City, near the line where California meets Oregon. Most people on land slept right through it. Then, roughly 2 hours later, a second quake, a magnitude 5.2, struck closer in, off the small town of Petrolia. A smaller shock followed within the half hour. That made 3 jolts before breakfast, spread across 3 different cracks in the same restless patch of coast. If you find these calm late-night reports useful, you can subscribe and stay with us. If you live up there, your phone may have buzzed with a warning seconds before the ground moved. No one was hurt and no wave came. Even so, this short string of quakes is worth a closer look because of where it landed. This is the most seismically active corner of the West Coast, sitting right beside the fault that could one day produce the big one. This report walks through what shook, why it shook, and what it does and does not tell us about what comes next. The first shock came in the dark, well before sunrise. Out under the Pacific, about 100 miles west and a little north of Crescent City, California, a patch of seafloor gave way. The break measured magnitude 5.7. It happened near the place where the California coast hands off to Oregon, far enough out that the nearest people were asleep in their beds on land. A magnitude 5.7 is a real earthquake, not a faint tremor. In a city it can crack plaster, knock cans off shelves and rattle nerves. This one spent most of its strength on open water and empty seafloor. The break sat about 6 miles below the surface, which is shallow as these things go. Shallow quakes deliver more of their punch to the ground above, but here that ground was the ocean floor, miles from any town. So the morning began quietly on land. A few people near the coast stirred. Some felt a slow roll, the kind that makes a hanging lamp sway rather than a picture fall. Many slept straight through it and learned about the quake later, from a phone alert or the morning news. There was no damage to speak of and no one was hurt. For the scientists watching the live feeds, though, the quake stood out the moment it arrived. It was one of the larger earthquakes recorded anywhere in the world that morning, and it landed in a spot they watch more closely than almost any other stretch of American coast. That single fact, the location, is what turned an ordinary offshore quake into something worth a longer look. The instruments told the story fast. A dense web of seismometers lines this coast, and they pinned the break to the Gorda Plate, a slab of ocean floor wedged into one of the most crowded geological corners on the continent. We will come back to that plate and why it breaks so often. For now, the point is simple. The quake did not strike at random. It struck inside a system that has been grinding and cracking for a very long time. There is a habit, when a quake hits near a famous fault, of reaching straight for the worst case. It helps to slow down instead. This break was offshore, it was moderate in size, and it caused no harm. The right first move is to describe it plainly and get the facts straight before reading anything larger into it. So here are the plain facts of that first jolt. A magnitude 5.7, about 100 miles out from Crescent City, roughly 6 miles deep in the early hours, felt lightly on land, with no injuries and no damage. No tsunami warning went out, and the sea stayed calm. By any normal measure, the morning could have ended right there, as a single offshore quake worth a line in the regional news. It did not end there. The ground was not done for the day. What put the word cluster in the headlines was that the 5.7 turned out to be the opening note rather than the whole song. Within a few hours, the same corner of coast would shake again, on a different fault, in a way that caught more attention than the first. It helps to picture the place. Imagine the far northwestern coast of California, where the redwoods come almost to the water and small towns sit between the sea and the mountains. Crescent City near the Oregon line, Eureka and Ferndale and Petrolia to the south. This is a beautiful, lightly populated stretch, and it happens to sit on top of one of the busiest earthquake machines in the country. The people who live there know it. Many of them have felt the ground move more than once. That first shock was a knock on a door these communities know well, and a second knock was already on its way. The second quake arrived a couple of hours after the first, with the sky just starting to lighten. This one struck closer to shore, about 40 miles west of the small town of Petrolia on the southern Humboldt coast. It measured magnitude 5.2. Where the first break sat far out near the Oregon border, This one landed nearer the homes and roads of the north coast, and more people felt it. It also struck on a different fault. The first quake broke inside the Gorda Plate. This second one was tied to the Mendocino Fault, a long crack in the seafloor that runs east to west, out past Cape Mendocino. Two quakes, a couple of hours and a few dozen miles apart on two separate faults, in the same early morning. That pairing is what started people using the word cluster. Then came a third. About 26 minutes after the 5.2, the same area gave a magnitude 4.5. A quake that size is a solid shake up close and a gentle nudge farther away. Coming so soon after the 5.2 and in the same spot, it read as an aftershock, a smaller adjustment as the ground settled into its new position. A quick word on the numbers themselves. Early magnitudes are first estimates, and they get revised as more data comes in. The second quake was first reported by some sources near magnitude 5.1 and settled close to 5.2. That kind of small revision is routine, and not a sign of anything wrong. It is simply the difference between a fast first read and a careful second one. The shape of the morning does not change with 1/10 of a point either way. So by mid-morning the tally stood at 3 notable quakes: a 5.7 far offshore on the Gorda Plate, a 5.2 closer in on the Mendocino Fault, a 4.5 aftershock right behind it. Smaller shakes flickered through the area too, the ordinary background chatter of a busy fault zone, most of them too faint to feel. Here is why the second quake drew more notice than the first, even though it was a touch smaller. The 5.7 spent itself on open water far from town. The 5.2 sat closer to the coast, so its shaking reached more people and more buildings before it faded. A quake loses strength quickly as it travels, like the warmth from a fire that you feel on your face up close and barely sense across the room. Move the same quake nearer to people, and it feels like more. Even so, the second quake did no real harm. There were reports of a light to moderate shaking along the coast, the sort that sets dishes clinking and wakes light sleepers. No buildings came down, no injuries were reported, and again, no tsunami warning, because of the way these particular faults move, which we will get to shortly. What we had, by the end of the morning, was a tight little burst of energy from one stretch of coast. 3 quakes you could feel, on at least 2 faults, inside a few hours. That is more than this area produces on a quiet day, and it is exactly the kind of pattern that makes a person stop and wonder whether something larger is building underneath. That wondering is fair, and we will take it seriously. The deeper question sat underneath the whole morning, the same one the scientists were turning over as they watched the feeds. 3 quakes in a single morning on a coast like this one. The honest answer depends on what a cluster actually is, and on how this particular ground usually behaves. A cluster, in plain terms, is a group of earthquakes that happen close together in time and close together in space. Instead of one quake, and then a long quiet, you get several in a row, packed into hours or days, within the same patch of ground. The morning's burst fit that shape. 3 felt quakes and a scatter of smaller ones, one morning, one corner of coast. Scientists sort these groupings into a few families, and the difference between them matters. The most common pattern is a main shock followed by aftershocks. One large quake breaks the rock, and the ground around the break keeps adjusting for a while, sending out smaller shakes that fade over days or weeks. The 4.5 that morning, right after the 5.2, behaved like a textbook aftershock. A second pattern is the swarm. In a swarm, there is no single dominant quake. Instead, a flurry of similar-sized shakes comes through, often driven by fluids or magma moving underground, with no clear leader and no obvious main event. Swarms are common near volcanoes and in certain geothermal areas. The morning sequence does not look like a swarm. It had a clear largest quake, the 5.7, and the others trailed below it. But it carried a twist. The 5.7 and the 5.2 were not on the same fault, and they were dozens of miles apart. That makes the link between them looser than a simple main shock and its aftershocks. They may have nudged one another, or they may have been 2 separate releases of strain that happened to land on the same morning. Both readings are reasonable, and the honest answer is that we cannot be sure which it was. That uncertainty is normal, and it is worth sitting with rather than rushing past. The ground does not announce its reasons. We see the quakes on the instruments, we map where they sat, and we infer the rest. When 2 moderate quakes strike the same region hours apart on different faults, Telling a true causal story from a coincidence is genuinely hard. What we can say is that this region produces clusters often. The corner of coast off Cape Mendocino is one of the most seismically active places in California, and that is not a guess. It is a measured fact, drawn from decades of records. The faults here are packed tightly together. The rock is under heavy strain from several directions at once, and quakes here come in bunches more readily than they do in calmer ground. There is an interesting wrinkle in the research too. A study published this year looked closely at how earthquakes group near the Mendocino Triple Junction. It found that the area has a very high rate of background quakes, the steady drumbeat of small shaking that never stops. But it also found that big quakes here tend to spawn relatively few aftershocks compared with other parts of the West. In plain words, the ground here is always busy, yet it does not always pile on long aftershock sequences the way you might expect. That mix makes each cluster a little harder to read, so the word cluster by itself does not tell you whether to worry. A cluster can be the ground quietly releasing strain in small doses, which is in a sense a good thing. A cluster can also, much more rarely, be the early stir before a larger quake. Most clusters are the former. A few in hindsight were the latter. The trouble is that they can look alike while they are happening. This is the heart of why the quakes drew attention without drawing alarm from the experts. The pattern was real and a touch above the usual pace. The location was serious. But the behaviour, 3 moderate quakes in a morning on a famously restless coast, fell within the range of what this ground does. It was notable. It was not on its face a clear signal of something bigger on the way. To go further than that, you have to leave the quakes themselves for a moment and look at the stage they played out on. The reason this coast shakes so much is written into its geology, and once you see the layout, the morning makes more sense. It starts with a meeting point out past Cape Mendocino, where 3 great plates come together at once. Off Cape Mendocino, on the far northern coast of California, 3 of the planet's great plates meet at a single point. Geologists call it the Mendocino Triple Junction. It is one of the few places on Earth where 3 plate boundaries come together, and it is the engine behind nearly every quake on this coast, including the morning's cluster. Picture the map. The Pacific Plate carrying much of the ocean floor grinds northwest along the edge of the continent. The North American plate sits under the land, and wedged between them, small and battered, is a third slab called the Gorda Plate. Where these 3 press against one another just offshore, the rock has no easy way to move. Something has to give, and it gives us earthquakes. Each pairing of plates has its own fault, and at the Triple Junction, 3 major fault systems run right up to the meeting point. To the south stretches the San Andreas Fault, the long crack that runs down through California toward Los Angeles. Running east to west out to sea is the Mendocino Fault, where the second quake struck, and to the north begins the Cascadia Subduction Zone, the giant offshore fault that reaches all the way to Canada. 3 of the most consequential faults in North America, all converging on one stretch of water off a quiet redwood coast. That convergence is why this spot shakes the way it does. Most places sit on one fault, or near one boundary. Here, the strain of 3 different plate motions piles into a small area at once. The ground is pushed, dragged, and bent from several directions in the same patch of crust. Quakes can break on any of the 3 systems, or inside the plates themselves, which is exactly the spread we saw that morning. 1 quake in the Gorda Plate, 1 on the Mendocino Fault. The numbers bear out how busy this place is. Across the broader region, instruments record thousands of small quakes a year, most far too faint to feel. A magnitude 5 quake comes along roughly every couple of years, a magnitude 6 lands every several years, and a magnitude 7, a genuinely major quake, strikes this corner about once every 2 decades on average. By the standards of the United States, that is a remarkable pace. Few places on land are this active. It helps to think of the Triple Junction as a busy intersection with no traffic lights. 3 streams of traffic, each moving a different way, all trying to pass through the same crossing. Most of the time, the cars thread past one another in small, constant adjustments, the background quakes that never stop. Now and then, 2 streams jam, and the pressure releases in a larger break. The morning's cluster was a modest jam, cleared in a few hours with no wreck. This setting also explains why a cluster here is less surprising than it would be elsewhere. On a single quiet fault, 3 felt quakes in a morning would be unusual and worth real concern. At a triple junction, with 3 fault systems and 3 plates all active at once, the odds of several quakes landing close together go up. There is simply more machinery to move. That does not make a cluster meaningless. It does mean you read it against a backdrop of constant motion rather than against silence. The triple junction has another feature that matters for the coast. It is migrating. Over millions of years, the meeting point has been creeping slowly northward, leaving a trail of older faults behind it on land. This long, slow march has shaped the mountains and valleys of Northern California, and it keeps the whole region geologically young and restless. The coast you see today is a snapshot of a process still very much in motion. For the people who live here, none of this is abstract. They feel the intersection working under their feet. Towns like Ferndale and Rio Dale and Petrolia sit almost on top of the junction, and they have ridden out major quakes within living memory. The cluster was a light tap from a machine these communities know can hit much harder. To understand the first and largest of the quakes, we need to look at one piece of this intersection in particular. Not a fault, but a plate. The smallest of the 3, the one doing much of the breaking, the much-abused slab called the Gorda Plate. The Gorda Plate is the runt of the Pacific Northwest plates, and it pays for its size. It is a slab of ocean floor tucked into the corner off Northern California, hemmed in by larger plates on every side. The first and largest quake, the 5.7, broke inside it. To understand that quake, it helps to understand why this little plate is so prone to cracking. Most earthquakes happen on the boundary between 2 plates, where their edges grind past or under each other. The Gorda Plate is different. A great many of its quakes happen inside the plate, not just along its rim. The slab itself is being squeezed and bent out of shape, and it fractures internally to cope. Geologists describe it as one of the most deformed plates on the planet, and the 5.7 was a piece of that internal breaking. The reason is pressure from several sides at once. The Gorda Plate is slowly sliding eastward and downward beneath the North American plate, a process called subduction, at a rate of about 1 inch a year. That alone would strain it. But it is also being shoved by the larger Pacific plate to the south, and pinched by the geometry of the corner it sits in. Imagine a small block of soft wood clamped in a vise and pushed from a third direction by a hand. It will not just move, it will split. The Gorda Plate splits. That inch a year sounds like nothing, and over a single year it is nothing you could see. But rock does not give smoothly. It holds and holds, building strain like a bent stick, until it snaps and lets go all at once. The snap is the earthquake. Decades of slow squeezing can release in a few seconds of shaking. The 5.7 was one such release, a long build-up spent in a moment, 6 miles under the sea. Because so much of the Gorda Plate's breaking happens within the slab, its quakes are scattered rather than lined up neatly on one fault. They pepper the offshore area in a way that can look messy on a map. This is part of why clusters form here so readily. There is no single clean fault doing all the work. There are many smaller fractures threading through a slab that is coming apart under strain. History shows how much energy this small plate can hold. Some of the strongest quakes on this coast have come from the Gorda Plate or its immediate surroundings. Major breaks here have reached magnitude 7, large enough to do real damage on land when they strike close enough. The 5.7 was modest by that measure, well short of those big events, but it came from the same straining slab and broke for the same reasons. There is a useful point hiding in all this. A quake inside the Gorda Plate is not the same as a quake on the Great Cascadia Fault that lies nearby. They are different events with different causes. The Cascadia Subduction Zone is the boundary where whole plates lock and then lurch in rare, enormous quakes. The Gorda Plate breaking inside itself is a smaller, more frequent kind of event. Both happen in roughly the same neighbourhood, which is why news of one can be mistaken for a sign of the other. The morning's 5.7 was the smaller internal kind. That distinction is not a technicality. It changes what the quake means. An internal Gorda break, even a felt one, does not load the Great Cascadia Fault in any direct, simple way. It is the everyday business of a plate under pressure, not a hand on the trigger of the big one. Saying so is not meant to wave the danger away. It is meant to keep the danger in its right place, which is the only way to think about it clearly. So the largest quake of the morning was the Gorda Plate doing what it has done for ages. Squeezed past its strength, it cracked, sent out a moderate shake and settled. far out to sea, 6 miles down with no one near enough to be harmed. The second quake was a different animal. It did not break inside a plate. It broke on a boundary between plates, on the long east to west crack called the Mendocino Fault. That fault moves in its own particular way, and the way it moves is the reason the sea stayed calm all morning. The Mendocino Fault runs out to sea from Cape Mendocino, heading roughly west, marking the southern edge of the Gorda Plate. The second quake, the magnitude 5.2, broke along it. This fault moves in a way worth understanding, because the way it moves shaped the whole morning, including the fact that no wave came. On the Mendocino Fault, the two sides slide past each other horizontally. One block grinds west, the other east, and they scrape along their shared edge. Geologists call this strike-slip motion. The famous San Andreas Fault moves the same way, sliding sideways rather than up and down. When the Mendocino Fault slips, the ground mostly shifts side to side, not up or down. That sideways motion is the key. The seafloor lurches horizontally, but it does not rise or drop much, and it is the sudden rise or fall of the seafloor that shoves the water above into a tsunami. A sideways slip moves the water far less, like sliding your hand flat across the surface of a full bathtub rather than pushing it down from above. The first makes ripples. The second makes a wave that sloshes over the rim. So when the 5.2 broke on the Mendocino Fault, the seafloor slid sideways and the ocean above barely noticed. No significant water was displaced. The National Tsunami Warning Center, which watches every quake that could threaten the coast, saw the size and the type of motion and issued no warning. The sea stayed flat. For a coast that has heard real tsunami warnings before, that quiet was a relief, and it was expected given the kind of fault that moved. The Mendocino Fault is one of the busiest faults in the region. It takes up much of the grinding between the Gorda Plate and the Pacific Plate, and it produces frequent quakes, most of them moderate and offshore. A 5.2 here is a normal day's work for this fault. It has produced larger. The reason this particular one drew notice was its timing, arriving the same morning as the Gorda Plate's 5.7 and its closeness to shore. It is worth pausing on how close to shore that second quake sat. About 40 miles out is near enough that coastal towns felt clear shaking, yet far enough that the energy had spread and softened before it reached them. The people of Petrolia and the surrounding coast felt a definite jolt and roll, the kind that stops a conversation and makes everyone glance at the ceiling. Then it passed. Nothing fell that could hurt anyone. The fault had done this many times before, and the towns had ridden it out many times before. Strike-slip faults like the Mendocino can still be dangerous when they are large and close. A big sideways quake can shake hard enough to topple chimneys and crack roads, even without a tsunami. The strong sequence near Petrolia in 1992 proved that, but a moderate 5.2 40 miles offshore simply did not carry that kind of force to land. It was felt, noted and survived without harm. Understanding the fault type also helps make sense of the cluster as a whole. The morning's two main quakes broke in two different ways. One was the Gorda Plate cracking inside itself, a vertical leaning internal break. The other was the Mendocino Fault sliding sideways, a horizontal break on a plate edge. Two different mechanisms, hours apart in the same crowded corner. That mix is typical of this junction, where several kinds of faulting sit side by side and can all let go in the same stretch of time. So the lack of a tsunami was not luck, it was physics. A sideways slipping fault and an internal plate break, neither of which lifted the seafloor enough to move the ocean. Had a different fault moved, the great offshore subduction zone for instance, the morning could have read very differently. That difference between fault types is one of the most important things to grasp about this coast, because it separates the quakes that merely shake from the ones that can send water. It is worth slowing down on that point, because the tsunami question is the one that frightens people most about this coast. A tsunami begins with the seafloor moving up or down. When a quake suddenly lifts or drops a wide slab of ocean bottom, it lifts or drops all the water sitting on top of it. That displaced water has to go somewhere, so it spreads outward as a long, low wave that can travel across an entire ocean and rise up tall when it reaches shallow coast. The size of the wave depends on how much seafloor moved and in which direction. This is why the type of fault matters so much. A fault that slides sideways, like the Mendocino Fault, moves the seafloor side to side and lifts very little water, a fault that thrusts, where one block rides up and over another, can heave a huge stretch of seafloor upward in seconds. Thrust faults are the great wave makers. Sideways faults rarely are. The morning's quakes were a sideways slip on the Mendocino fault and an internal break in the Gorda plate. Neither lifted a broad section of seafloor, so neither moved enough water to matter, and no warning went out. The physics gave the answer before any person had to make a call, and the warning centre's decision matched it. The faults that do make great tsunamis on this coast are the subduction zones, where one plate dives beneath another. The Cascadia Subduction Zone, just to the north, is exactly that kind of fault. When a subduction zone of that size finally lets go, it can thrust up a vast length of seafloor at once and send a tsunami racing towards shore within minutes. That is the scenario the region prepares for, and it is a genuinely serious one. We will come to Cascadia in its own right later, because it is the larger shadow behind every quake on this coast. For the cluster, though, the calm sea was the expected and correct outcome. It is important not to let relief tip into the wrong lesson. The absence of a tsunami did not mean the quakes were trivial, and it did not mean the coast is safe from tsunamis in general. It meant only that these particular quakes, on these particular faults, were not the kind that lifts water. A different quake, on the wrong fault, would tell a different story. People who live on this coast are taught a simple, reliable rule for the day a real wave is coming. If an earthquake is so strong that it is hard to stand, or if the shaking goes on for a long time, that is the natural warning. The right response is to move to high ground or inland as soon as the shaking stops, without waiting for an official alert, because a locally generated wave can arrive faster than any siren. For a Great Cascadia quake, the first waves could reach the nearest beaches within roughly 15 to 30 minutes, and the closest stretches even sooner. None of that applied that morning. The shaking was light to moderate on land and brief. No one needed to flee, and no one did. But the rule is worth repeating in calm times, because it is the kind of knowledge that only helps if it is already in your head when the ground starts to move. Coastal communities here run drills and post-evacuation routes for exactly that reason. So the story of the missing wave is really a story about reading the ground correctly. The instruments measured the size of each quake, the depth, and the direction of slip, and from those they could tell within moments that no dangerous wave would form. That speed is not an accident. It is the product of a monitoring system built up over decades, watching this coast every second of every day. That same system did something else remarkable that morning, something many residents experienced directly. Before the shaking from the larger quakes reached them, some people's phones lit up with a warning. Some residents of the north coast got a few seconds of warning before the ground shook, delivered straight to their phones. It came from a system called ShakeAlert, run along the west coast by the United States Geological Survey and its partners. ShakeAlert detects a quake the instant it begins, and warns people a little farther away before the shaking reaches them. It cannot predict earthquakes in advance, which is a different thing that no system can do. What it offers is warning of a quake already underway. The trick rests on a race between two things. An earthquake sends out energy in waves, and the waves travel at different speeds. The first to arrive is a faster, gentler wave that does little damage. Behind it comes a slower, stronger wave that does the shaking you feel. Electronic signals, meanwhile, travel at nearly the speed of light, far faster than either wave, so when sensors near the quake catch that first fast wave, they can fire off an alert that races ahead and reaches more distant phones before the strong shaking gets there. The warning is short, often just seconds, but seconds are enough to do something useful, enough to take cover under a sturdy table, enough for a surgeon to lift a scalpel away, or for a train to start braking before the worst arrives. The system is not magic, and it is not long notice. It is a brief, precious head start, and it grows longer the farther you are from the quake. That morning, the larger quakes were far enough offshore that the system had time to work for many people on land. Sensors out near the coast caught the breaks, calculated their size and location in a heartbeat, and pushed alerts inland. Some people felt their phones buzz with the warning, and then, a moment later, felt the gentle roll arrive, exactly as designed. For a quake that did no harm, it was a quiet proof that the system works. People receive these alerts in a couple of ways. There is a dedicated app called MyShake, built for the purpose, which many West Coast residents have installed. And there are the wireless emergency alerts, the same channel that carries weather warnings and missing person notices, which can push a quake alert to phones in the affected area even without any app. Together they put the warning in a lot of pockets at once. It is worth being honest about the limits. If you're very close to the quake, right on top of where it breaks, the warning and the shaking arrive almost together, and you may get no useful lead at all. The system trades distance for time. The closer you are to the danger, the less notice it can give. For the worst shaking nearest the break, ShakeAlert helps least. That is not a flaw so much as a law of physics the system cannot beat. Still, the value over a whole region is real. For a major quake on this coast, ShakeAlert could give cities tens of seconds of warning, time to slow trains and let millions of people take cover before the worst shaking arrives. The cluster was a low-stakes rehearsal for that day, a chance to see the machinery run when nothing was on the line. There is something steadying in that. The same density of instruments that makes this coast so well studied also makes it among the best warned in the world. Every small quake that flickers across the sensors is also a test of the system, a confirmation that it is watching and ready. The morning's quakes were caught, measured, and broadcast within moments, and the people who needed to know knew. That speed of measurement points to a question people often ask when the alerts go out and the news lists the numbers. What a magnitude 5.7 actually means, set against a 5.2 or against the great quakes the region fears, is not as simple as those small numbers make it sound. When the news says a magnitude 5.7 and then a magnitude 5.2, the two sound almost the same, a few tenths apart. The magnitude scale hides a lot inside those small steps. It is built so that each whole number up means a quake about 32 times stronger in the energy it releases. The scale is not a simple ruler, it climbs steeply. Start with the two main quakes. The 5.7 released more energy than the 5.2, even though the numbers look close. Half a point on the scale is roughly a five-fold difference in energy. So the morning's largest quake was several times more powerful than its near twin, which is part of why it counted as the main event, even though the second one was felt by more people. Size and felt strength are not the same thing, because distance changes what reaches you. Now stretch the scale upward, and the steepness becomes startling. A magnitude 6 is not a little stronger than a magnitude 5. It releases something like 32 times more energy. A magnitude 7 is 32 times more than a 6, which makes it around 1,000 times more than a 5. And a magnitude 9, the size the Great Cascadia Fault could one day produce, releases on the order of 1,000,000 times more energy than the moderate quakes of that morning. That last comparison is worth letting land. The quakes that shook the coast that morning felt but harmless sit about 1,000,000 times smaller in energy than the worst case the region prepares for. The same coast, the same general neighbourhood, can produce events so far apart in scale that they hardly belong in the same conversation. A moderate quake and a great one are different in kind, not just in degree. This is why scientists are careful not to treat a moderate cluster as a small version of the big one. It is not a big quake in miniature. It is a different thing entirely, separated from the great quakes by factors of thousands or millions in released energy. A run of 5s tells you the ground is active, which everyone already knew about this coast. It does not tell you a 9 is loading. The steepness of the scale also explains why magnitude 7 quakes here are such serious events when they strike close to land. A 7 is roughly 1,000 times more energetic than the morning's quakes. The region has produced 7s within living memory, and they have cracked roads, toppled chimneys, and rattled towns hard. When you hear that this coast averages a magnitude 7 about every couple of decades, that is the weight behind the number. Not a stronger version of June, but something in a different league. There is a second number that often rides alongside magnitude, and it measures something different. Magnitude describes how much energy the quake released at its source. Intensity describes how strongly the ground actually shook at a given place. A large quake far away can produce low intensity where you stand, while a moderate quake right under your feet can produce high intensity. The morning's quakes were moderate in magnitude, and because they were offshore, low to moderate in intensity on land. Both facts are true at once, and holding them together is the key to reading any earthquake report. So the plain translation of the numbers is this: 2 moderate quakes, the larger several times stronger than the smaller, both far below the major quakes this coast has seen, and all of them a vast distance in energy from the great quake the region fears. Felt, measured, and harmless. That is the honest scale of the morning. One more factor shaped how the quakes felt on land, beyond their magnitude and their distance from shore. It is how deep below the surface they broke. A quake that breaks shallow, and one that breaks deep, can carry the same magnitude and yet reach the surface very differently. The first quake broke about 6 miles beneath the seafloor. By the standards of earthquakes, that is shallow. Quakes can break anywhere from just under the surface to hundreds of miles down, and the depth changes how the shaking arrives at the top. A shallow quake and a deep one of the same size can feel quite different to the people above. A shallow break has less rock between it and the surface. Its energy arrives with less distance to spread and weaken, so the shaking right above can be sharp and strong. A deep break, by contrast, has to send its energy up through many miles of rock first. That energy spreads out and softens on the way, so a deep quake often feels broader and gentler at the surface, though it can be felt over a wider area. Depth is one of the dials that sets how a quake feels. That morning, the shallow depth of the quakes would normally have meant sharp shaking nearby. What spared the towns was not depth, but distance. The quakes were shallow, yes, but they were also far offshore, the larger one about 100 miles out and the second about 40. So the sharp, near-source shaking spent itself on open water, and only the softened, travelled-out edge of it reached land. Shallow but distant. The two factors pulled against each other, and distance won. This coast produces both shallow and deep quakes, and the difference is tied to the geology underneath. The shallow quakes tend to break in the upper crust, and along the plate edges near the surface, like the Mendocino fault slip. Deeper quakes break within the subducting slab as it bends and descends, sometimes tens of miles down. Those deep slab quakes are a known hazard in the Pacific Northwest, capable of strong shaking over a wide region even from far below. The morning's quakes were the shallow kind, born near the surface in the crowded upper layers of the junction. Depth also feeds into the tsunami question we walked through earlier. A shallow quake on the right kind of fault can deform the seafloor more directly, since the break is close to the surface. That is one more reason subduction quakes are such efficient wave makers, as they break along a shallow, gently sloping contact and can lift the seafloor over a wide area. The morning's quakes, shallow as they were, still did not raise a wave, because their motion was sideways or internal, rather than the broad upward thrust that moves water. For the scientists, the depth was one more line in the quick profile they built of each quake within moments of its striking. Size, location, fault type, direction of slip, and depth. Together, those numbers told them almost immediately what kind of event they were looking at and what it could and could not do. A shallow, moderate, sideways or internal break offshore. No wave, no major damage felt on land. The profile was complete and reassuring before most residents had finished their coffee. It is easy to lose the human scale in all these measurements, so it helps to come back to it. 6 miles down is roughly the cruising height of a jetliner turned downward into solid rock and seafloor. That is where the larger quake began, in the dark and the pressure, a slab of ocean floor finally slipping after years of strain. The energy raced upward and outward from there, through rock and water, weakening as it spread until it reached the coast as a gentle roll that woke a few light sleepers. That picture of energy spreading out from a point far offshore and arriving softened on land leads naturally to the question of who actually felt the quakes and where. The reach of the shaking, mapped from thousands of reports, traces the size and depth and distance of the quakes in a way the raw numbers cannot. When a quake strikes, the United States Geological Survey collects reports from ordinary people who felt it. Through a simple online form, anyone can say where they were and how strong the shaking seemed. Thousands of these reports pour in after a felt quake, and together they draw a map of the shaking that the instruments alone cannot. The morning's quakes drew their own scatter of reports across the north coast. The pattern was about what you would expect from offshore quakes of this size. The shaking was felt across coastal northern California and into southern Oregon, strongest near the coast closest to the breaks and fading inland. Near the shore, people described a clear jolt and roll, enough to wake them or stop them mid-task. Farther inland, the reports thinned to a faint sway, a hanging plant moving, a sense that something had passed. Beyond a certain distance, nothing at all. The first quake, far out near the Oregon border, was felt only lightly on land, and many people slept through it entirely. It struck in the small hours when most of the coast was asleep, and its distance offshore softened it further. The second quake, closer in and a little later in the morning, reached more people awake and aware, which is part of why it left a stronger impression even though it was smaller. Timing and distance shaped the human experience as much as raw size did. These felt reports are more than a curiosity. They are real data. By gathering where people felt strong or weak shaking, scientists can map how the energy spread and check it against their models. The reports help confirm the quake's location and size, and they reveal how local ground conditions change the shaking. Soft valley soil can amplify a quake, while hard bedrock can mute it. So two towns the same distance away can report very different experiences. The crowd becomes part of the instrument. For most people on the coast, the felt experience was mild and brief. A few seconds of motion, a moment of attention, and then it was over. No one reported injury. The damage reports that sometimes follow a quake, of cracked walls or fallen shelves, did not come in any number that morning. The shaking was within the range these communities feel from time to time and shrug off. There is a particular character to feeling an offshore quake that residents of this coast know well. The motion often arrives as a slow rolling sway rather than a sharp jolt, because the sharper, higher frequency shaking fades fastest over distance, and the slower, longer waves carry farther. So a distant offshore quake tends to feel like a gentle heave, a sensation more than a slam. The morning's quakes, travelling tens of miles to reach land, arrived in just that softened, rolling form for most who felt them. It is worth noticing how routine the whole experience was for the people who live there. A quake wakes you. You wait to see if it grows. It does not, and you go back to sleep or back to your morning. Children on this coast learn the drill in school. Adults have felt dozens of these over the years. The cluster, for all the attention it drew elsewhere, was for many locals just another morning when the ground reminded them where they live. That gap between how the cluster looked from far away and how it felt up close is the heart of the matter. From a distance, 3 quakes in a morning near a famous fault can read as alarming. On the ground, it read as a familiar coast doing a familiar thing. Both views are real, but only one of them is grounded in how this place actually behaves. And that brings us to the honest question at the centre of this whole report, the one the title raises directly. Here is the honest answer, stated plainly. For this particular stretch of coast, a cluster of moderate quakes in a single morning is not, by itself, abnormal. This is the most seismically active corner of California, and one of the most active in the country. The ground here moves constantly. Several felt quakes close together is well within the range of what this junction produces in the course of a normal year. That deserves to be said clearly, because the framing around clusters can run ahead of the facts. The instruments record thousands of quakes a year in this region, the great majority too small to feel. Felt quakes come along regularly. A magnitude 5 lands roughly every couple of years, and the area has absorbed magnitude 7s within living memory. Against that backdrop, 3 moderate quakes in a morning is a busy day, not a break from the pattern. So in what sense was the cluster worth a second look? In a few real ones, and it helps to name them precisely rather than vaguely. The quakes came in a tight burst, on more than one fault, with the largest among the bigger events recorded worldwide that day. That combination is uncommon enough to notice, and the location, right at the southern doorstep of the Cascadia Subduction Zone, gives any activity here an added weight that activity elsewhere would not carry. The cluster was real, a little above the everyday pace, and parked next to the most consequential fault in the region. That is enough to study it closely without inflating it. What the cluster was not, on the evidence, is a clear warning of a larger quake on the way. Most clusters in active zones are simply the ground releasing strain in moderate doses, and that is the most likely reading here. The research on this junction, fresh this year, adds a useful detail. It found that while the region has a very high rate of background quakes, its larger events tend to produce relatively few aftershocks compared with other parts of the West. So the ground here is restless by habit, yet it does not always escalate. That pattern argues for calm attention rather than alarm. It also helps to separate two different feelings that get tangled together. One is the natural unease of feeling the Earth move and seeing a map dotted with markers off your coast. The other is the actual measured hazard, which scientists track with long records and careful math. The unease is understandable and human. The measured hazard, for a moderate offshore cluster like this, did not spike. Both can be true. Feeling worried and being in immediate danger are not the same thing, and on this morning the worry ran ahead of the risk. None of this is meant to dismiss the coast's real dangers. They are serious, and we will spend the second half of this report on them, because the larger faults nearby can produce truly great quakes, and the region is right to prepare. The point is narrower and more useful. This specific event, this cluster of moderate quakes on this morning, was an ordinary expression of an extraordinary place. The place is genuinely dangerous over the long run. The morning on its own was not. That distinction between a dangerous place and a dangerous day is the steadiest way to hold all of this. The coast off Cape Mendocino will keep producing clusters like this one for as long as those three plates keep grinding, which is to say for ages to come. Some mornings will bring a few moderate quakes and nothing more. A handful of mornings, across the long span of years, will bring something far larger. Telling those mornings apart before they happen is beyond anyone right now. To see why the place earns its serious reputation, even when a given morning does not, it helps to look back. This coast has a long memory, written in its quakes. The moderate cluster sits in a line of events stretching back decades, some of them gentle like this one, some of them powerful enough to shake whole towns. That record is where the real measure of this coast lives. This coast keeps a long record of its own shaking, and the moderate cluster takes its place near the bottom of a list that runs much higher. To understand why scientists watch this corner so closely, it helps to walk back through the quakes it has produced, the ones that did real damage and the ones that came close. Start with 1992. A strong sequence struck near Petrolia, the same small town off which the morning's second quake broke. The main shock reached magnitude 7.2, and it was followed by large aftershocks over the next day. Buildings were damaged, fires broke out, and the ground along the coast was lifted in places, a vivid reminder that this junction can produce major quakes, not just moderate ones. The Petrolia sequence is still a reference point for the region, a measure of what the faults here can do when they let go in force. Move forward to 2010. A magnitude 6.5 struck offshore near Eureka, the largest town on this stretch of coast. It snapped power lines, toppled chimneys, broke windows, and knocked out electricity to tens of thousands of people. No one was killed, but the damage ran into the millions, and it rattled a city that thought it knew earthquakes. A 6.5 is far smaller than a 7.2, yet close to a population centre, it was enough to do real harm. Then a cluster of events in recent years brought the hazard close again. In late 2021, two quakes near magnitude 6 struck within seconds of each other off Cape Mendocino, widely felt but causing only minor damage. Exactly 1 year later, in late 2022, a magnitude 6.4 hit near Ferndale, and that one bit hard. The shaking in the small town of Rio Del was violent, and it left tens of millions of dollars in damage to homes and buildings. 2 people died in connection with that quake. For a magnitude in the 6s, it was a costly, painful event, and it showed how much a moderate quake can do when it strikes directly beneath a town. That string of events tells you something the morning's gentle cluster could not. The difference between a quake felt and a quake that ruins a winter is mostly a matter of distance and location. The morning's 5.7 and 5.2 were larger than or close to the size of the 2010 Eureka quake, yet they did no damage at all because they broke far offshore. The Ferndale quake was smaller and broke right under a town. Where a quake strikes matters as much as how big it is, and sometimes more. There is a pattern in these dates worth sitting with. Petrolia in 92, Eureka in 2010, twin quakes in 2021, Ferndale in 2022, and, as we will come to, a major offshore quake in 2024. This coast does not go quiet for long. It produces a felt quake often, a damaging one every few years, and a major one every couple of decades. The morning's cluster was simply the latest entry in a ledger that never closes. The people who live here carry this history in their bones. Older residents remember 92. Almost everyone remembers the recent run of quakes, because they were close enough together to feel like a season rather than scattered events. Each one taught the same lesson in a slightly different way. The ground here is patient and then sudden, quiet for a stretch, and then awake, and the only sure thing is that it will move again. That history is also why the local emergency systems are as developed as they are. Towns along this coast have evacuation routes posted, schools run earthquake drills, and many homes keep supplies ready for the days after a major quake when help may be slow to arrive. This is not anxiety. It is the ordinary prudence of people who have learned what their ground can do and have decided to be ready for it. So the moderate cluster sits in a long line, near the gentle end of it. The same faults that produced it have, in living memory, produced quakes 1,000 times more powerful in the energy they released. That is the real reason a morning of moderate shaking draws a careful eye here. It is a small move by a system known to make large ones. The most recent of those large moves came just a year and a half before this cluster, and it is worth revisiting in full because it shows what this coast looks like when the ground does more than stir. The most recent major quake on this coast struck in late 2024, and it reached magnitude 7. It broke offshore near Cape Mendocino, along the easternmost part of the Mendocino Fault, the same fault system that produced the morning's smaller 5.2. A magnitude 7 is roughly 1,000 times more energetic than the moderate quakes of that morning. It is the kind of event the region treats as a genuine emergency, and for a few hours it was treated as exactly that. The quake ruptured a long segment of the fault, around 30 miles of it, in a sudden sideways slip. The shaking spread across the north coast and was felt far inland. Within 15 seconds of the break, the ShakeAlert system pushed warnings to phones from the San Francisco Bay Area up to southern Oregon, telling people to expect strong shaking. For many, those few seconds of notice arrived before the ground did, a real-world demonstration of the warning system working at scale. Then came the part that frightened people most. About 5 minutes after the quake, the National Tsunami Warning Center issued a tsunami warning for a stretch of the California and Oregon coast. Sirens sounded in some towns. People near the water moved to higher ground. Schools and offices emptied toward evacuation routes. For a tense stretch, the coast braced for a wave. The wave did not come. Within roughly an hour, the warning was cancelled. The reason traces straight back to the physics we walked through earlier. The 2024 quake, like the morning's 5.2, was a sideways slipping break on the Mendocino Fault. It moved the seafloor side to side rather than thrusting it upward, so it did not displace enough water to raise a dangerous tsunami. The warning had been issued out of proper caution, on the first read of a large offshore quake, and lifted once the analysis confirmed the motion was the kind that does not make a great wave. The damage on land, for a magnitude 7, was relatively modest, and the reasons are worth understanding. The quake broke largely offshore, sparing the towns the worst of the near-source shaking. The region is lightly populated, so there were fewer buildings in harm's way than there would be near a city, and the building stock here is shaped by hard experience with quakes. Even so, there was damage. A chimney toppled in one town, windows broke, goods were thrown from store shelves, a road was damaged by the shaking, one injury was reported. For a quake of that size, the coast got off relatively lightly, helped by geography and by readiness. That event, only a year and a half before the morning's cluster, is the right frame for understanding the cluster. The same fault system that produced a magnitude 7 and a tsunami warning in 2024 produced a magnitude 5.2 and no warning in June. Same neighbourhood, same kind of fault, vastly different scale and outcome. The cluster was the quiet cousin of the 2024 quake, born of the same machinery, releasing a tiny fraction of the energy. It also explains why the region reacts the way it does to offshore quakes now. The memory of the 2024 tsunami warning is fresh. People remember the sirens and the scramble to high ground, and they remember that the wave did not come. That memory cuts both ways. It keeps people alert and ready to move, which is good. It can also breed a dangerous complacency, a sense that warnings are false alarms, which is the one lesson the coast cannot afford to learn. The next warning could be the real one. The 2024 quake, large as it was, still came from the smaller class of faults on this coast. It was the Mendocino Fault sliding, not the Great Subduction Zone rupturing. As serious as a magnitude 7 is, it is not the largest quake this region can produce, not by a wide margin. The truly great quake, the one the whole Pacific Northwest prepares for, comes from a different and far larger fault that begins just to the north of all this activity. That fault is the reason a moderate cluster here makes national news, and it deserves a clear, calm look. Just north of the Mendocino Triple Junction begins one of the largest faults in North America, the Cascadia Subduction Zone. It runs offshore for about 620 miles, from Northern California up past Oregon and Washington to Vancouver Island in Canada. It is the great shadow behind every quake on this coast, and it works in a fundamentally different way from the faults we have discussed so far. Cascadia is a subduction zone, which means one plate is sliding beneath another. Offshore, the Juan de Fuca plate and its neighbours, including the small Gorda plate, are diving slowly eastward under the much larger North American plate. The boundary where they meet is not a vertical crack, but a vast, gently sloping contact, hundreds of miles long, where the two plates are pressed together. For most of the time, that contact is locked. The plates are stuck, unable to slide past each other smoothly. While the boundary is locked, the plates keep moving far below, and the strain builds. The edge of the continent is slowly squeezed and bent, storing energy like a giant spring being wound tighter year after year. This goes on for centuries. Then, all at once, the locked contact gives way along a huge length of the fault, the spring releases, and the result is a megathrust earthquake, the most powerful kind the planet produces. When Cascadia ruptures fully, it can reach magnitude 9 or greater. That is around 1,000,000 times more energetic than the moderate quakes of that June morning, and many times larger than the magnitude 7 of 2024. The shaking from a full Cascadia rupture would not last seconds, as the morning's quakes did. State emergency planners estimate it could last for 5 to 7 minutes along the coast, an almost unimaginable stretch of continuous violent motion. Few people living have felt anything remotely like it. Because Cascadia is a thrust fault, lifting a vast slab of seafloor upward in one motion, it is exactly the kind of fault that makes great tsunamis. A full rupture could send waves that, in the worst stretches, reach tens of feet high, with some estimates running far higher in narrow inlets. And because the fault sits just offshore, those waves could reach the nearest beaches within roughly 15 to 30 minutes, far too fast to wait for an official alert. The shaking itself would be the warning. This is why a moderate cluster at Cascadia's southern doorstep draws the attention it does. The morning's quakes did not happen on Cascadia, and they do not directly load it. But they happened right beside it, in the restless junction where Cascadia meets the other faults. Any activity in this neighbourhood is read against the possibility of the great fault next door, even when the activity itself is small and unrelated. The proximity is what turns a regional quake into national news. It is important to hold the relationship between these faults clearly. The Gorda plate breaking inside itself and the Mendocino fault sliding sideways are not the same as Cascadia rupturing, and a moderate quake on them is not a countdown to the big one. Scientists do study whether quakes in this junction could, in principle, influence the southern end of Cascadia, and it is an open question. But there is no evidence that the morning's moderate cluster moved Cascadia toward rupture. The honest position is that the great fault remains where it has long been, locked and loading, neither calmed nor triggered by a morning of moderate shaking nearby. What makes Cascadia so sobering is not any single recent quake. It is the long, quiet record of what it has done before, and the knowledge that it has been silent for a very long time. The last time the great fault ruptured along its full length, it left marks up and down the coast and sent a wave clear across the Pacific Ocean. That event happened more than 3 centuries ago, and the story of how we came to know its exact date is one of the most remarkable pieces of detective work in all of Earth science. The last great Cascadia earthquake struck on the evening of the 26th of January in the year 1700. We know the date that precisely, even though no one in the Pacific Northwest wrote it down at the time, and the way scientists pinned it down is a story worth telling slowly. The first clue came from across the ocean, in Japan. Japanese records from that era are detailed and well kept, and they describe a tsunami that struck the coast in late January of 1700. The strange thing about this wave was that no one in Japan had felt an earthquake before it arrived. A tsunami with no local quake puzzled the people who recorded it. Generations later, scientists gave it a name. They called it the orphan tsunami, a wave with no parent earthquake anywhere nearby. The mystery held until researchers connected the Japanese wave to evidence on the other side of the Pacific. Along the coast of the Pacific Northwest, geologists had found signs of sudden, drastic change. There were ghost forest stands of dead cedar trees killed when the land dropped abruptly, and salt water drowned their roots. There were layers of marsh soil buried suddenly under sand, the mark of a coast that had sunk in an instant and been swamped by the sea. The land itself recorded a great quake, even if no written account survived. One scientist found a particularly clear piece of the puzzle by digging in a coastal marsh. Beneath a layer of sand, he uncovered a band of old marsh soil with the remains of a marsh plant still in it. Plants that had grown at the surface and then been dropped below the tide line in a single event. That sudden drop sealed under sand was the fingerprint of a great earthquake lifting and dropping the coast. The buried soils could be dated, and they pointed to around the year 1700. The final step joined the two sides of the ocean. A researcher studying the Japanese tsunami records worked backward from the timing of the wave. A tsunami crosses the Pacific at a known speed, so the arrival time in Japan could be traced back to when the wave must have started on the far side. The math pointed to the night of the 26th of January 1700 in the Pacific Northwest, about 9 in the evening local time. The orphan tsunami had found its parent. The quake that drowned the cedar forests and the wave that struck Japan were the same event, a full rupture of the Cascadia Subduction Zone. There was one more source of memory, older than any of the science. The native peoples of the Pacific Northwest carried oral histories of a great shaking and a flood that came in the night, passed down through generations. Stories from many different coastal nations told of the ground heaving and the sea rushing in, of villages lost in the dark. When scientists gathered these accounts, they matched the timing and the place of the 1700 quake. The land, the trees, the Japanese records and the human memory all told the same story. That convergence of evidence is what gives the 1700 date its rare certainty. Most prehistoric quakes are known only within a range of decades or centuries. Cascadia's last great rupture is known to the night, and the deeper record, read from layers of seafloor sediment laid down by past quakes, shows that Cascadia has ruptured many times before, on average every few hundred years, sometimes more often and sometimes less. The arithmetic of that record is what keeps scientists watching. It has now been more than 300 years since the last full rupture, which is well within the range of Cascadia's typical intervals between great quakes. The fault is not overdue in any precise sense, because these intervals vary widely, and the fault keeps no schedule. But enough time has passed that another great rupture is a real possibility within the lifetimes of people now living. That possibility is usually expressed as a probability, and it is worth stating that number plainly, without dressing it up or playing it down. Scientists put the odds of a great Cascadia earthquake in plain figures, and the most commonly cited one is this. There is roughly a 10 to 15% chance of a magnitude 9 rupture of the full Cascadia Subduction Zone in the next 50 years. Some studies, looking at partial ruptures of the fault's southern end, put the chance of some major Cascadia quake higher, closer to 1 in 7 over the same period. These are the honest numbers, and they are worth understanding for what they do and do not say. A 10 to 15% chance over 50 years is not small, and it is not a certainty. Turned around, it means there is roughly an 85 to 90% chance that the full fault does not produce a magnitude 9 in the next 50 years. Both halves of that sentence are true, and people tend to hear only one of them depending on their mood. The calm way to hold it is to treat the risk as real and worth preparing for, while not living each day as though the quake were imminent. It might happen this year. It very probably will not. Both can be true at once. It helps to compare the number to other risks people accept without much thought. A 10 to 15% chance over 50 years is the kind of odds that justifies insurance, preparation, and sound building codes. The same way people prepare for fires or floods that may never come. It does not justify fear or upheaval. It is a planning number, not an alarm. The right response to it is the dull, useful work of being ready, not the sharp feeling of dread. The same body of research lays out other regional risks that often get less attention than the great offshore quake. there is a high chance, estimated around 85% over 50 years, of a strong deep earthquake beneath the Puget Sound region of Washington, the kind that breaks within the descending slab tens of miles down. There is a meaningful chance of a damaging shallow quake on the crustal faults that run directly beneath cities like Seattle. These closer, smaller quakes may actually be more likely to harm a given person in their lifetime than the rare great rupture, simply because they happen more often and can strike right under populated ground. That is a useful corrective to the way the hazard is usually discussed. The magnitude 9 megathrust captures the imagination, and it should, because its scale is staggering. But the everyday earthquake risk on this coast is carried more by the moderate and strong quakes that come every few years and the deep slab quakes that strike cities than by the once-in-centuries giant. The morning's cluster, ironically, was a small sample of that everyday risk, the steady background against which the rare great quake will someday stand out. There is a hard limit running underneath all of these numbers, and it must be stated clearly. No one can predict the exact time or place of any earthquake. This is not a temporary gap in knowledge that better instruments will soon close. It is a settled position, stated plainly by the United States Geological Survey, that earthquake prediction, in the sense of a specific date and location, is not possible with current science and may never be. What scientists can do is estimate probabilities over years and decades, map where quakes are likely, and warn in the seconds after one begins. What they cannot do is tell you that a quake will strike a certain place on a certain day. That limit is why the probabilities matter so much. In the absence of prediction, the percentages are the best tool there is for making sound decisions about building codes, insurance, and preparation. They let a society act wisely on a threat it cannot time. The 10 to 15% figure is not a disappointment standing in for a real forecast. It is the real forecast, and it is enough to guide good choices. The picture grew more complicated this year, with new research suggesting that the Great Quake, when it comes, might not arrive alone. A study published just weeks before the cluster raised the possibility that two of the West Coast's major faults could rupture in close succession, turning a single regional disaster into something larger and harder to respond to. That work is worth understanding because it changes the shape of the worst case. A study published this past spring by researchers at Oregon State University raised a sobering possibility. Two of the most dangerous fault systems on the West Coast, the Cascadia Subduction Zone and the northern San Andreas Fault, may be able to rupture in close succession, triggering each other within minutes to hours. The two faults meet near the Mendocino Triple Junction, the same crowded corner where the morning's cluster struck, and the new work suggests they may sometimes speak to each other. The evidence comes from the long sediment record on the seafloor. Each great quake shakes loose underwater landslides that settle into distinct layers, and by reading and dating those layers, scientists can reconstruct the timing of past ruptures on both faults. The lead researcher found that in 3 cases over the past 1500 years, including the Great Quake of 1700, the record suggests Cascadia and the northern San Andreas ruptured within minutes to hours of each other. Pinning down such tight timing in centuries-old layers is difficult, and the researchers are careful about it. But the pattern appears more than once. The idea that one fault could trigger another is not far-fetched. When a great quake ruptures, it sends powerful waves of energy through the crust and shifts the stress on nearby faults. A neighbouring fault already near its breaking point could be pushed over the edge by the passing of those waves or by the sudden change in stress. The two faults meeting at the Triple Junction are close enough, and the energy of a great rupture large enough that such a nudge is physically plausible. Real-world examples of this kind of fault conversation are rare but real. The clearest came from Sumatra, where a massive quake in 2004 was followed by another great quake on an adjacent fault segment about 3 months later. Scientists have long suspected that faults can interact this way, but firm, documented cases have been scarce. That scarcity is part of why the Cascadia and San Andreas finding matters. It adds evidence to a process that has been more theory than observation. The implication for the West Coast is serious, and the researcher behind the study put it in stark terms. A great quake on either fault alone would strain the entire nation's emergency resources to respond. If both ruptured in the same brief window, the disaster would strike multiple major regions at once. Instead of one catastrophe to focus on, there could be several unfolding together, with San Francisco, Portland, Seattle, and Vancouver all thrown into emergency in a compressed span of time. The response, already daunting for one great quake, would be stretched across a far wider front. It is important to be precise about what this research does and does not say, because it is easy to misread. It does not say that such a double rupture is likely soon, or that the morning's cluster was a sign of it. It says that the two faults appear capable of syncing up, and that they may have done so a few times in the deep past. It is a finding about the shape of the worst case drawn from history, not a forecast that the worst case is near. The probabilities for Cascadia we discussed still stand. This work adds a dimension to them rather than raising them. Set against the moderate cluster, the new research is a study in scale and distance. The cluster was 3 moderate quakes in a morning, harmless, on the small faults of the junction. The research concerns the rare, great ruptures of the 2 giant faults that meet nearby, events separated from the cluster by 1,000,000 times in energy and by centuries in timing. The two share a map and almost nothing else. The cluster is the everyday hum of the junction. The double rupture is its rarest and most extreme possibility. What ties them together is the place. The Mendocino Triple Junction is where the small faults chatter constantly, and where the great faults meet and may one day speak together. That same crowded geology produces both the harmless morning cluster and the theoretical doomsday scenario, which is why a single corner of quiet coastline carries such an outsized place in the science. And it is why even the smallest quakes there are studied so carefully, because the tiniest tremors can reveal how the whole machine is put together. Most of the earthquakes on this coast are far too small to feel, and for a long time they were treated as background noise. That is changing. Scientists have begun mining the steady stream of tiny quakes, the ones below the threshold of human sensation, and finding that they carry a wealth of hidden information about how the ground beneath Northern California is built and how it moves. Earlier this year, researchers reported that by tracking swarms of these minuscule tremors, far too weak for anyone to notice, they had uncovered a hidden and surprisingly complex earthquake zone beneath Northern California. The faults down there turned out to be more intricate than the simple map suggested, a tangle of small structures all quietly active. The tiny quakes, taken one by one, mean nothing. Taken together, by the thousands, they trace the shape of the faults the way iron filings trace the lines of a magnet. The reason this is possible now comes down to better listening. Modern seismic networks are dense and sensitive, and new computer methods can sift through enormous catalogues of tiny quakes that older techniques would have missed or ignored. Where a scientist once saw a handful of notable quakes, an algorithm can now find tens of thousands of faint ones, and the pattern they form reveals faults and processes invisible at the larger scale. The ground has been whispering all along, and we have finally built ears fine enough to hear it. This matters for reading clusters like the mornings. The felt quakes. The 5.7 and the 5.2 are the loud notes. Around and beneath them runs a constant murmur of tiny shaking, and the character of that murmur can tell scientists whether a region is simply ticking along normally, or doing something unusual. After the morning's cluster, researchers would have looked not only at the 3 felt quakes, but at the swarm of small ones around them, checking whether the background activity matched the ordinary pattern or departed from it. The tiny quakes also offer a window into processes that larger quakes hide. Slow, quiet movements deep on the faults, the shifting of underground fluids, the gradual loading of one fault by another, all of these can show up first as subtle changes in the smallest tremors. In some subduction zones, scientists have found slow slip events, episodes where part of the fault creeps silently over days or weeks without a felt quake, releasing strain quietly. Watching the tiny quakes is one way to catch these hidden motions in the act. None of this amounts to prediction, and it is worth saying so plainly to avoid raising false hope. Reading the small quakes tells scientists more about how the faults are arranged and how they behave, but it does not let them forecast the next large quake's time and place. The hard limit still holds. What the fine-grained listening provides is understanding, a clearer map of a complicated machine, which over time makes the probability estimates and hazard maps more accurate. It sharpens the long view, not the short one. There is something fitting in the fact that the smallest quakes are teaching the biggest lessons. The The morning's cluster drew attention because 3 of its quakes were large enough to feel and to notice. But the deeper knowledge of this coast is being assembled from the millions of quakes no one feels at all. The faint and constant signal that the dramatic quakes interrupt. The felt cluster was a moment. The unfelt murmur is the long conversation, and it is the one scientists most want to understand. That gap between the felt and the unfelt, between the moment and the long conversation, mirrors a gap in how people experience all of this. A felt quake lands as an event, sudden and a little frightening. The quiet, constant risk it represents is much harder to feel. Understanding why a brief cluster frightens people more than a far larger long-term threat says as much about us as it does about the ground. A cluster of quakes frightens people in a way that a statistic never will, and the reason has more to do with how the human mind works than with the actual danger. 3 quakes in a morning is something you can feel, picture, and point to on a map. A 10 to 15% chance over 50 years is an abstraction. The mind reaches for the vivid thing and shrinks from the abstract one, even when the abstract one carries the greater weight. This is a well-known feature of how people judge risk. A sudden, dramatic, recent event feels far more threatening than a slow statistical one, regardless of which is actually more likely to harm you. A cluster of earthquakes near a famous fault is about as vivid as a hazard gets. It arrives in the night, it shakes your home, your phone lights up with warnings, and the news fills with maps of dots off your coast. Of course it frightens. It is built almost perfectly to trigger alarm. The proximity to Cascadia sharpens the effect. People on this coast have heard for years that a great quake is coming, and they carry that knowledge as a low background worry. When the ground actually shakes near that fault, the worry surges to the front of the mind and attaches itself to the quakes in front of them. The brain draws a line from the small felt event to the great feared one, even when no such line exists in the geology. The morning's cluster became, for many, a stand-in for the big one, a rehearsal of a dread already present. The recent history feeds it too. The tsunami warning of 2024 is fresh in memory, with its sirens and its scramble to high ground. So when quake struck again, the body remembered the last time and braced. That is not irrational. It is the mind doing exactly what it evolved to do, treating a recent danger as a likely repeat. The trouble is that the geology does not work the way memory does. The ground has no sense of recent events and no momentum toward a repeat. Each quake breaks on its own terms. There is a real cost to letting the vivid crowd out the statistical. People who are frightened by a harmless cluster may exhaust their worry on the wrong thing and grow numb to the warnings that matter. Or they may come to see all the alerts as noise, the way the unfulfilled tsunami warning can make the next one easier to ignore. Misplaced fear does not make anyone safer. It tends, over time, to make them less prepared, because fear burns out and leaves complacency behind. The healthier response runs the other way. Feel the natural unease of a felt quake, let it pass, and channel whatever attention it raised into the dull, durable work of preparation. The cluster, in that sense, can serve a useful purpose. It is a free reminder, costing no damage and no injury, to check the emergency kit, review the evacuation route, and secure the heavy furniture. A harmless quake that prompts a household to prepare for a dangerous one has done a quiet favour. This is the steadying frame the whole report has been building toward. The danger on this coast is real but slow, large but rare, and best met with steady readiness rather than spikes of fear. A cluster of moderate quakes is a poor guide to the real risk, because it speaks to the part of us that fears the vivid, not the part that plans for the likely. Reading it correctly means feeling the jolt, setting it down, and turning to the work that actually helps. To do that, it helps to be precise about what a cluster like this can and cannot tell us, so the attention it draws gets spent wisely. It is worth being precise about what the morning's cluster can and cannot tell us, because precision here is the difference between useful attention and wasted fear. Start with what it can tell us. It confirms that this stretch of coast remains seismically active, which was never in doubt. It shows that the faults of the Mendocino Triple Junction continue to release strain in moderate quakes, which is their normal behaviour, and it gives scientists fresh data, 3 well-recorded quakes and a swarm of smaller ones, to refine their understanding of how this junction works. Now the harder part, what it cannot tell us. It cannot tell us that a larger quake is coming. A cluster of moderate quakes is not a reliable warning sign of a great one. The vast majority of such clusters, in this region and around the world, are followed by nothing larger. They are the ground releasing strain in small amounts, and that release is, if anything, the ordinary and healthy behaviour of an active fault zone. Reading a moderate cluster as a countdown to disaster is a mistake the evidence does not support. The deepest reason for this caution is the one stated earlier and worth repeating. No one can predict the timing and place of a specific earthquake. There is no known pattern of small quakes that reliably precedes a large one. Scientists have searched hard for such precursors for decades, and none has proven dependable. A cluster might, in rare hindsight, turn out to have come before a larger quake. But while it is happening, there is no way to tell a harmless cluster from a meaningful one, because they look the same. This is genuinely frustrating, and it is better to admit the frustration than to paper over it with false reassurance or false alarm. People naturally want a cluster to mean something, to be a signal they can act on. The honest truth is that it is mostly noise, with no readable message about the future. The science can describe what happened with great precision and say almost nothing certain about what comes next. That gap between hindsight and foresight is the central hard fact of earthquake science. There is one narrow exception worth noting to be fair to the full picture. Immediately after a moderate quake, there is a slightly raised chance of another quake nearby in the short term, simply because aftershocks follow quakes, and one quake can stress an adjacent fault. This is why, in the hours and days right after a cluster, scientists watch closely, and the odds of further shaking are modestly elevated. But this is a small, short-lived effect, measured in a few percent over days, and it fades quickly. It is not a sign of a great quake building, it is just the ordinary settling of disturbed ground. So the right reading of the morning's cluster is narrow and clear. It was a real but ordinary expression of an active fault zone. It does not forecast a larger quake. It does not move the long-term odds for Cascadia in any measurable way. It does refine the science a little and remind everyone where they live. And it leaves the future exactly as uncertain as it was before the ground shook, no more readable and no less. That conclusion can feel unsatisfying because it offers no prediction and no all clear. But it is the truthful one, and there is a kind of steadiness in accepting it. The coast will keep shaking, mostly in small ways, occasionally in large ones, on a schedule no one can read. The only sound response to a threat you cannot time is to be ready for it whenever it comes. That readiness is not complicated, and it is the one place where ordinary people have real power over this risk. It is worth laying out plainly what being ready actually means. For people who live on this coast, the most useful response to a cluster like this is not worry, but preparation, and the steps are well established and within anyone's reach. They come straight from official guidance, and none of them requires predicting anything. They simply make a household ready for the quake that will, someday, come. Start with the action to take during the shaking itself. The standard guidance taught in schools and drills across the West Coast is 3 words: drop, cover, and hold on. Drop to your hands and knees before the shaking knocks you down. Take cover under a sturdy table or against an interior wall, protecting your head and neck, and hold on to your shelter until the shaking stops. The old advice about doorways is outdated. A sturdy table is better. The goal is to keep from falling and to shield yourself from things that fall. For anyone near the coast, there is a second rule that can save a life, and it concerns tsunamis. If an earthquake is strong enough that it is hard to stand, or if the shaking lasts unusually long, that is the natural warning of a possible tsunami. The right response is to move to high ground or inland immediately after the shaking stops, on foot if roads are blocked, without waiting for any official alert. A locally generated wave can arrive within 15 to 30 minutes, faster than warnings can reach everyone. The ground's own shaking is the signal to move. Before any quake comes, there is preparation that pays off later. Secure the heavy things that can fall and hurt someone. Tall bookcases and cabinets can be strapped to wall studs. Water heaters can be braced. Heavy items can be moved off high shelves, especially above beds. These are small projects done once that quietly remove some of the most common causes of injury when the ground moves. Keep supplies for the days after a major quake, when normal services may be slow to return. The standard recommendation is enough water and food for each person for at least several days, along with a flashlight, a battery or hand crank radio, a first aid kit, any needed medications, and sturdy shoes kept by the bed. After a great quake, help may take time to arrive, and roads and power may be down. A prepared household can care for itself in the gap and ease the load on emergency services stretched thin. There is also the matter of insurance, which is easy to overlook and important to consider calmly. Standard homeowner policies generally do not cover earthquake damage, a fact that surprises many people only after a quake, when it is too late. Separate earthquake coverage exists, and whether it makes sense depends on a household's situation and finances. This is not advice to buy it, only a prompt to know where you stand before the ground moves, so the decision is made in calm rather than in crisis. Finally, make a simple plan with the people you live with. Agree on where to meet if you are separated. Choose an out-of-area contact everyone can call since local lines may be jammed, and make sure everyone, including children, knows the drop, cover and hold on routine and the tsunami rule. None of this takes long. A single afternoon can put a household in far better shape than most, and the peace of mind that follows is itself worth the effort. The thread running through all of it is calm readiness, the opposite of both panic and denial. The cluster harmed no one, but it offered a free and timely nudge to do these ordinary things. A household that responds to a harmless quake by checking its supplies and reviewing its plan has turned a moment of unease into something genuinely protective. That is the best possible use of a morning like this one. While individuals prepare their homes, scientists keep their own kind of watch over the coast, and it is worth knowing what they are actually looking for in the weeks after a cluster. After a cluster like this one, scientists do not simply move on. They keep a close watch on the coast through a dense network of instruments, looking for any sign that the ground is doing something out of the ordinary. Understanding what they monitor and what they are looking for shows both the strength and the limits of the science as it stands today. The backbone of the watch is the seismometer network, hundreds of sensitive instruments along the coast that record every quake, down to the faintest tremor. In the days after the cluster, these instruments track the aftershocks and the background activity, checking whether the rate of small quakes returned to normal or stayed elevated. A quick settling back to the usual hum is reassuring. A continued high rate would prompt a closer look. After this cluster, the activity behaved as it normally does, tapering as aftershocks faded. Alongside the seismometers run instruments that measure the slow deformation of the ground itself. Networks of precise satellite positioning stations fixed to the earth along the coast can detect movements of a fraction of an inch, tracking how the land is being squeezed and bent as the plates press together. These measurements reveal the build-up of strain on the great faults over years, and they can sometimes catch the slow, silent slip events that release strain without a felt quake. They are how scientists watch the spring of Cascadia winding, even when no quake is happening. There are seafloor instruments too, a harder and newer frontier. Much of the action on this coast happens offshore, beyond the reach of land-based sensors, so scientists have worked to place instruments on the seafloor itself, including along the Cascadia Fault. These underwater sensors and cabled observatories extend the watch out to where the great quakes will actually begin. They are expensive and difficult to maintain, but they fill a gap that land instruments cannot, listening to the fault where it lies. What are they all listening for? In the immediate term, they watch the aftershock sequence for anything unusual, such as activity migrating toward a major fault or a rate that climbs rather than falls. Over the longer term, they track the steady accumulation of strain, refine the maps of where faults lie and how they connect, and watch for the rare, slow-slip events that may signal stress transferring through the system. Each piece adds to the long-term picture, the probability estimates and hazard maps that guide how the region builds and prepares. It is important to be clear, once more, about what this watching can deliver. It cannot produce a prediction of the next great quake's date and place, and the scientists running the network are the first to say so. What it can do is detect a quake the instant it begins, and warn through ShakeAlert, track the long build-up of strain to keep the probability estimates honest, and deepen the understanding of how this complicated coast works. The watch is real and valuable. It is simply aimed at understanding and rapid warning, not at the prediction that physics does not allow. There is a steadiness in knowing the watch never stops. Every second of every day, the instruments are listening, the data are flowing to the agencies that track them, and the systems that would warn the coast in the first moments of a great quake are armed and ready. The morning's cluster was caught, measured, and understood within moments, and then folded into the long record that makes the next assessment a little sharper. That quiet, constant vigilance is the real reassurance this coast can offer, more than any forecast could. It is the appropriate place to draw the threads of this whole story together and look plainly at where things stand. So where does the morning's cluster leave us, set against everything around it? 3 moderate quakes struck off the far northern coast of California in a single morning. A magnitude 5.7 far offshore in the Gorda Plate, a magnitude 5.2 closer in on the Mendocino Fault, a magnitude 4.5 aftershock right behind it, with a scatter of smaller shaking around them. No one was hurt, no building fell, no wave came, the sea stayed calm and the towns carried on. That is what is known, and it is worth holding on to the plain facts before reaching for anything larger. The cluster was real, a touch above the everyday pace, and it landed in the most seismically active corner of the west coast, right beside the Great Cascadia Fault. The quakes broke on the small faults of the junction, not on Cascadia itself. They moved in ways that do not raise tsunamis. They were caught by the instruments and broadcast by the warning system within moments, and some residents got their few seconds of notice exactly as the system is built to give. Here is what remains uncertain, stated honestly. We cannot say with confidence whether the 2 main quakes truly triggered one another or simply struck the same morning by chance. We cannot say what the coast will do next week or next year, and above all, no one can predict the timing and place of the next great quake, on Cascadia, or on any of the faults that meet at this restless junction. The science describes the past with growing precision, and the future only in probabilities. That gap is the hard, permanent fact at the centre of all of this. What the cluster was not is a warning of a larger quake on the way. The honest reading, the one the evidence supports, is that it was an ordinary expression of an extraordinary place. This coast produces clusters like this as a matter of course, because 3 great plates grind together just offshore, and the rock breaks under the strain. The morning was a small move by a system known to make large ones, and the smallness of it is the truth the title's alarm runs past. The next thing to watch is not a single quake, but the long, patient build-up that the instruments track day after day, the strain accumulating on Cascadia, the slow deformation of the coast, the steady murmur of small quakes that reveals how the faults are arranged. None of it will announce the great quake in advance. All of it sharpens the picture and keeps the region's preparations grounded in the best understanding there is. The watch goes on, and it will be there, listening, on whatever morning the ground finally does more than stir. For the people who live on this coast, the lesson of the cluster is the same one it has always been, delivered gently this time at no cost. The ground here will move again. Most of the time it will be like this morning, felt and harmless, a reminder more than a threat. Now and then, across the long span of years, it will be far more. The way to meet a danger you cannot time is to be quietly ready for it, and then to live without fear in the meantime. That balance of readiness without dread is the steadiest ground a person can stand on here. We will keep watching this coast and report back when there is something real to tell. Until then, stay prepared, stay calm, and rest easy tonight. The instruments are listening, even while you sleep.